All right, dear student. So far we have learned about London dispersion forces, and we know that they have temporary dipoles. By the way, just for you to know, what does dipole means? Dipole means, let me draw in here. So it means two poles, like a north and south pole, and one pole should be positive, another pole should be negative. So this is called like a north and south pole from geography, but in chemistry, we know that one side should be negative, another side should be positive. Let's discuss about dipole-dipole bonding. I have given an example of HCl molecule again. We know that chlorine is more electronegative, so the electrons will be closer to the chlorine. So let me show you in here. I have completed the Lewis dot and cross. They share their electrons, so the electrons are shared. We can see it in the middle. But as the chlorine is more electronegative, these electrons will be towards chlorine, so will come closer to chlorine. So it will be negatively charged, partial negative because there is an sharing still, sigma positive. But we know that dipole-dipole is intermolecular forces, so we need to draw at least two molecules nearby. What do we see in here? So the chlorine of HCl is sigma negative. It's always like that. Also, a hydrogen sigma positive. It is always sigma positive. So we are gonna have the attraction between these negatively charged and positively charged molecules, and it is intermolecular because it's between two molecules and it is permanent. Why this is permanent? Because whenever there is an hydrogen and chlorine, the electrons are always closer to the chlorine, especially these electrons are always closer to the chlorine. So what will happen? This will be negatively charged. By the way, you have to know that because we have the electrons even in here, around in here, sometimes the electrons are closer to this side, sometimes they are closer to this side, but still they will have a London dispersion forces too. But these forces are gonna be nothing compared to the in this case compared to the dipole-dipole permanent dipole-dipole forces. So this is called basically dipole-dipole forces. I have added note in here that in dipole-dipole interactions they occur between polar molecules. Let's review what does polar molecule means. Polar molecule means both sides, the end side, one end side should be positive and another end side should be negative for polar molecule. But in dipole-dipole, we have to know that this is dipole-dipoles are between non-polar molecules. Let's do examples in here. So oxygen 2. So let me draw two oxygen molecules. Oxygen O, we have double bonded and O2 because they have the same electronegativity, these two. So we will not have any polar molecule. So this is a non-polar. This is non-polar. Whenever the molecules are non-polar, the bonding in between will be London dispersion. I am going to write it as an LD. So let's take a look at carbon dioxide. Whenever we write the Lewis structure of that, and we know that oxygen is more electronegative than carbon, so it's gonna be sigma negative, it's gonna be sigma negative, it's gonna be sigma positive. As a molecule, you see, let me draw like that. You see one end is negative and another end is also negative. So this is non-polar molecule. So if I draw two CO2s nearby, so let me draw them, C, O, let me write sigma negative, sigma positive, sigma negative. Yeah, we are going to provide an electronegative chart for you. You see, both of them are negative, so we cannot have permanent dipole because they are going to repel each other. Instead, the electrons in here, they might change their places. So we have a temporary things, which is called London dispersion. But in an example of CO, let me write CO in here. By the way, CO has coordinate covalent bonding too. So oxygen is more electronegative than carbon. So one end is positive, another end is negative. So let me draw an adjacent molecule. So sigma negative, sigma positive, oxygen is sigma negative. So what we can say in here, we are gonna have permanent dipole in here. So it's gonna become dipole, dipole. Also in CO3 molecule, if we draw the Lewis structure, we are gonna see that uh, all the sides 2 minus. So let me write 2 minus, and we have some resonance structure, but we don't need to care about that. So sigma negative, sigma negative, sigma negative, sigma positive. You see, as a molecule, all the ends are negative. So this is nonpolar molecule. Now let's answer question number 2. It says molecular masses of ICl and brom2 are very similar, with their boiling points are 97.4 and 58.8. So I'm gonna write ICl in here, iodine and chlorine. Let me draw 2 iodine and chlorine, and let me draw bromine, 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 and bromine, bromine. So first of all, let's see, they have almost the same mass, so we can compare their boiling point, but they see that in ICl, we have definitely more boiling point than in bromines. It is 58.8 degrees Celsius. So where we should take a look, we should take a look at the electronegativity scale. So let's see iodine and chlorine. Iodine and chlorine. Iodine is 2.5, chlorine is 3. Let me write in here. So the chlorine is 3.0, iodine is 2.5, so it is 0.5, so it's an covalent polar molecule, polar bond. Now also what will happen, this is gonna be sigma negative, this one is sigma positive because it's more electronegative. So sigma positive, sigma negative. What we will have in between sigma positive and sigma negative, we are gonna have an permanent dipole. So this is called dipole-dipole interactions, but between two bromines, because each molecule, so this is polar, but bromines are non-polar. So if it is non-polar, it means that we cannot have dipole-dipole interaction. So this is non-polar. If it is not dipole-dipole interactions, we say that we have dipole-dipole. In general, remember, all molecules, this one, they have also dipole-dipole interactions, but in this one, because of the polarity, it has a permanent dipole-dipole too, so which increases the boiling point. Let's do quickly number 3, CH3CO, CH3. I'm gonna draw it like that, CH3 and CH3. Overall, we have in here sigma negative, sigma positive, because oxygen is more electronegative. And let me draw adjacent propanone molecule, CH3, double bond oxygen. We have sigma positive, we have sigma negative, but these ones will cancel each out. We don't need to worry about those. Overall, we have the polar molecules. So what will happen? We will have dipole-dipole interactions in here. Dipole, dipole. Also, we have London dispersion for sure because it's in all molecules. Thank you.